the the last idea in chapter 2, all of the sections in chapter 2 have this theme, have this goal. And the goal is how to solve a differential equation of order 1. That is, any differential equation that has as its highest derivative in it the first derivative. So of all of its various forms, how can we solve it? So we started in the beginning that we check to see if we can separate the variables. If so, that's the easiest form. If we can't do that, then the next step we check to see if it's exact. If it's exact, then there we integrate. You check that exactness criterion, and if that's the case, then you can integrate with respect to those differentials. Integrate with respect to dx. And if it has dy, integrate with respect to dy. So you check separation of variables first. Next thing we checked was to see if it's exact. Then the third thing that we said that if it's not separable, if the differential equation is not exact, then we ask the question, is it linear? And so then that's this previous section that we just got through looking at. If it's linear, we can write it in that form, find the integrating factor, and then we can solve based on this method. Now, there are two other things that we also check, and that is one is it homogeneous? And so that's the next thing we want to add, that objective students will be able to solve homogeneous differential equations, and also Bernoulli. It's kind of weird how they got this edition of the textbook, because Bernoulli typically follows right after the linear equation, because the Bernoulli form is that linear form. But you remember, I think somebody asked, what if you have y to some other power over there? Well, that's exactly what Bernoulli is saying. So it should follow right after the linear form. Homogeneous actually should come like right after separation of variables. So they have this edition. They have everything somewhat out of order, but it's okay. We'll try to manage. So first, talk about homogeneous equations. Homogeneous equations in the sense of a differential, because if it's a system of equations, then that idea of homogeneity means something completely different. This definition of homogeneity is actually from vector analysis. And that is that the forms of the expressions are said to gravitate or to have a uniform nature. In other words, if I have x squared y, that means that my power for just the variables, not the derivative, if it's x squared y, I'm thinking about a power of 3, some type of cubic form. Over here, I could have x to the third. That's still fine, because it's still in the idea of some cube form. There's 3 variables. So it could be y cubed, it could be x y squared, right? It could be y x squared, it could be x cubed. But as long as I have that consistency, we say then that it's homogeneous. That's all they're saying. All right. If the terms are linear, x and y, I want to still see x and y. If I see x and y, but over here I see x squared, then it's not homogeneous. See that? So either they're all linear, they're all quadratic, they're all cubic form, whatever. But if they're consistent, we say homogeneous. So the test of homogeneity here is that the function f of xy, if you can insert a parameter t with x and insert a parameter t with y, then if you can factor out that t to the nth from the function completely removing t from the function, so you have left t to the n times the function, the original function, and we say that the equation is homogeneous, and the order here is, or the degree is said to be n. I don't know if you recall, for those who've had linear algebra, when we got into the inner product spaces, and you had those axioms, and there was one axiom where this guy was stated. In other words, it said something like, if you have the norm of c times x, where c is a constant. The norm of c times x is equal to the absolute value of c times the norm of x. That was homogeneity. It's the same thing. If you have an inner product or if you have a norm, you should be able to factor. If there's a number, a constant number, multiplied to everything, can you factor out that number? That's that t to the n. Can I factor it out completely? If I can, then we say that the differential equation here is said to be homogeneous. If it is homogeneous, then we use what we call here an appropriate substitution. Either you let y equal to ux, or you let x equal to vy. Now, which one do you use? Now, I put this statement in here. Use the easiest of the substitution. In other words, count your dx's, count your dy's. If you have less dx's, then let x equal to vy. If you have less dy's, then you let y equal to ux. It helps in the simplification. So, but sometimes you may have two dx's, two dy's. Doesn't matter which one you use for the substitution, right? But if you have two dx's, three dy's, I'm gonna let x equal to vy because I have less dx's than I have dy's. Okay. Now, what if you don't use that? What if you just say every time I get the problem, I'm gonna always let y equal to ux, and people have done that. That's fine, but you may get a lot of terms that you end up having to, after you multiply them all out, maybe going back and canceling stuff out, but you'll get the same thing. I think this is just a note here for trying to find the easiest way to do it. Once you do that, once you simplify, funny thing is, this guy will go back to the book of Genesis, and because you're like in Revelation, and then you get to Genesis and say, hey, I'm here with all this complicated stuff, but I get back to what I first learned in section 2.1, 2.2. I can separate the variables. You solve by separating the variables after that. Okay? That's what happens with Genesis and Revelation. You get to Revelation, and you end up with this tree of life. You end up with everything that was back in the garden is also at the end. So it's just, where did we go? We just went back, right, to where it all was in the beginning. Let's look at a problem. So, hopefully I got time for maybe, I want to do two of these homogeneous problems and then one Bernoulli. So I may go over a couple of minutes. I hope that's okay. The chicken can wait. I want some chicken noodle soup. Nothing too heavy today. I've been trying to cut down on this. My wife said, "What are you doing to cut down?" Well, she said, "Are you exercising?" I used to. Okay. Anyway, it's too much personal information. X minus y dx parentheses then times dx plus x dy equal to 0. See how I was saying this is x to the first, y to the first, so it's linear. This is x, is homogeneous. If you go look at all the problems, this is x term, this is y to the first, x to the first, that's good, homogeneous. Look, this is y squared down there, so that's power of 2, yx, power of 2 again, x squared, power of 2. It's homogeneous. If this x squared dy was just x dy, it is not homogeneous. I can't solve using that method. And you just walk through all the problems, same thing, y minus x, same form, y plus x, same form. X, y squared, third power, right? Y to the third, x to the third. Do you see that? That's the idea of homogeneous. Now, my note here that use the easiest of the substitution if the x terms occurs the least in the problem, that is, and I'm really saying dx, if it occurs the least, then you use the x substitution. If the dy occurs the less, then I go back and modify that. I thought I had that there. But anyway, look at this. This is, I need my pen. This this is x dx minus y dx plus x dy equal to 0. Now, how many dx's do I have? 2. How many dy's do I have? 1. I'm going to let y equal to the least number of dy's. So let y equal to, and the substitution is already set, let y equal to ux, or let x equal to vy. So let y equal to ux. Just differentiate both sides here. So I get dy is equal to u dx plus x du. So I'm going to substitute. Wherever I have y, I'm going to write ux. Wherever I have dy, I'm going to write u dx plus x du. So this is x minus here y, or ux, parentheses, that's times dx, plus x times, parentheses, for the dy, that's u dx plus x du, that's equal to 0. You see what I mean? That you use the least number of, if you have dy with respect to dx, because in other words, look, I have 2 dx's, but I have 1 dy. If I let x equal to vy, it's going to give me dx is equal to a sum of two terms, right? So that dx would have to go here, so I have basically 2 terms times 2 terms. Now, you may have to get that, elsewhere, but if you can avoid that, why not avoid it? So here the multiplication is not too intense. So I'm going to simplify. This is x dx minus ux dx plus x u dx plus x squared du equal to 0. Now the negative ux dx cancels out with the xu dx. Right? So I have left x dx plus x squared du equal to 0. All right, we're going to separate. You can separate the variables. You can leave everything on one side if you want, or you can subtract, one term on the other side. Doesn't matter. Let's see if I can separate it just the way it is. In other words, divide through everywhere by the x squared. So when I do that, I have 1 over x dx plus du is equal to 0. Integrate. So this is the natural log of the absolute value of x plus u is equal to some constant. That u was y over x. That y is ux, excuse me. So u is y over x. So this is the natural log of the absolute value of x plus y over x is equal to c. Multiply everything by the x, so we get x times the natural log of the absolute value of x plus y is equal to c times x. Now you could have left it like this guy, and that would have been fine too. Any questions? Right. Number 3 is just like that previous one. Not too much going on there. Number 5 is good. 7 is good. 7 is good. It's probably good if I work number 7. So I'm going to just cross multiply, so I get y plus x times dy is equal to y minus x times dx. Notice here I have two dy's and I have two dx's, so it doesn't matter which one you use for the substitution. Now, whenever it's like that with me, if it doesn't matter which one, I always let y equal 2. So here, put y equal to ux. This implies that dy is equal to u dx plus x du. Just differentiate this term here. That's all we did. So I'm going to replace the y with ux. So we have ux plus x times that dy, that's in parentheses, u dx plus x du is equal to parentheses that y is ux minus x dx. Just simplify what we have. So we're going to FOIL. So this is u squared x dx plus u x squared du plus x u dx plus x squared du is equal to ux dx minus x dx. Now let's see. We have, this is xu dx, and that's ux dx, the same thing. If I subtract on both sides one time, they cancel out. Now, what I have here, I'm going to get the like terms together. I'm going to get the du's together, right? And then I get the dx's together. Excuse me. Try not to have a negative. I'm going to add this x dx to both sides. This is u squared x dx plus x dx, then plus this ux squared du, and this x squared du is x squared times parentheses u plus 1 times du is equal to 0. And we can do some factoring for these two dx's as well. So I can take out a x times parentheses u squared plus 1 dx plus x squared u plus 1 du equal to 0. Now, I want to separate the variables, get the like terms together. In other words, get the x's, dx's together, get the y's, dy's together. We'll get the u's, du's together. So this x that's here, he's good because he's associated already with dx. I got to get this x squared away from over there, so I'm going to divide everything by x squared. Now, this y plus 1 is good because he's associated with that d with u. This u plus 1 is good because he's associated with that du. But this u squared plus 1 is right here by the x dx, and that's not good. So I'm going to divide everything by the u squared plus 1, divide everything by the x squared. And so when I do, I have here 1 over x dx plus u plus 1 all over u squared plus 1 du is equal to 0. Divide everything by x squared, and then divided everything by that u squared plus 1. Okay? Now the variables are separable, so I'm going to integrate. We can break this up into two parts. This is u over u squared plus 1 du plus the integral of 1 over u squared plus 1 du is equal to the integral of 0 dx. See how I broke up this u plus 1 over u squared plus 1 as u over u squared plus 1, then plus 1 over u squared plus 1. Okay? That's legal. That's legal. I can do that. Right? So I integrate. So this is the natural log of the absolute value of x plus, I integrate this. This is a u du, if you will, but it's already a u divided by u squared plus 1. So if you let t equal to u squared plus 1, so dt is 2u du, so it has to be a 1/2 there. This is a 1/2 times the natural log of the absolute value of u squared plus 1, plus this is the tangent inverse of u, and that's equal to some constant. But we're not through. Right. Did everybody get that 1/2 natural log of the u squared plus 1? Because you got it. That's that u squared plus 1 downstairs. Its derivative here picks up the u du, but it also picks up an extra 2, right? A 2u du. So the 1/2 times the integral of dt divided by t becomes 1/2 times the natural log of t, where t is the u squared plus 1. Yes, well, yeah, you know, you think u du, but they're already using u, so I can't use that again, right? I can't use u again, right? So you can just use t dt or whatever, z dz, it doesn't matter. Exactly, they don't get mad. The variables don't, people do. Yes, they do. So multiply everything by 2. So this is 2 times the natural log. Let's finish this guy and we'll go home or get some lunch. The u is y over x, so this is y over x squared plus 1 plus 2 times tan inverse of y over x, and 2 times c is still a constant. Simplify this. This is the natural log of x squared plus the natural log of y squared plus x squared all over x squared plus 2 times tan inverse of y over x is equal to c. And this is the natural log of the absolute value of x squared plus y squared. Najra, get ready. They're about to run out of here. Plus 2 times. They're going to run out and they're going to change their major to business. Because they're saying, you got all this stuff here and you just get, what happened to the natural log of x squared and natural log of y squared plus x squared divided by x squared? And how did you just end up with the natural log of x squared plus y squared? Combine those natural logs, right? And so you multiply the natural log of x squared times y squared plus x squared divided by x squared. The x squares cancel out. Very good. Okay. So good. They're not going to change their major to business. We still got them. Yes, good. Y'all have a good one. Finish these problems for me. There's a couple of problems on the Bernoulli. I hadn't covered that. I'll cover that on Monday and review. Okay? Thank you.